There we go. All right. So just so everyone is aware, as some of you already heard me mention, right now there's a conflict with the Bio 101 series for winter quarter, Bio 103, which is part of first year bio if you're a bio major or a pre-med or anything like that. Right now there's a conflict with this class's lecture. The lab is scheduled on Thursdays from noon to 3. So like directly over the top of our lecture, which we should have caught, but because last year we try to arrange for as few conflicts as possible, because last year everything was online and we were letting people, watch lectures that were well recorded and do their lab activities whenever they wanted. It didn't matter. So we are fixing that now. The Bio 103 lab will move somewhere where it's not in conflict with this class. We don't know exactly what time that will be, but for now, if you're registering for 102, for Chem 102, go ahead and get registered. Pick your lab section. I'm told that the lab section on Tuesday, Thursday is already starting to fill up. So it's going to be mostly the people that are already in this class, but there's also going to be some people on the Tuesday, Thursday lab section for this class. That means that you're scheduling yourself from 10 to 12:30 to be in this lab, half-hour break, then 1 to 3 in this lecture, and then you finish this lecture and go straight to bio lab for another 3 hours. So doable, maybe not the most fun, and so weigh that when you're considering whether to do the Monday, Wednesday lab section or the Tuesday, Thursday. Might want to keep that in mind. All right, so there was a request to. Any other questions with regard to registering right now? Hopefully all of you are getting that all taken care of in anticipation of crushing the final in this class and being ready to move on to 102. Let me pull up the ICA so we can look at 2E. There it goes. All right, so we've got methane and propane being burned. It says we've got a mixture of methane and propane being burned in excess oxygen. We know that the total mass of methane and propane is 3 grams. So we're looking at this top section right here. So if the total mixture of methane and propane is 3 grams, and we have 2 different reactions happening. Right? So methane, CH4 gas plus O2 goes to CO2 and water. And when we balance this, we see, and that's balanced. Yeah. And then C3H8 plus, it's 5 O2, right? Yeah. Gives us 3 CO2 and 4 waters. Yes. All right. So what we're told in this problem is that we know the final ratio of water to CO2 when everything's done burning. If we didn't have any propane, then our ratio of CO2 to water at the end would just be 2 to 1. If we didn't have any methane and we only had propane, our final ratio would be 4 to 3. We're somewhere in between that. 1.75 is not the same as either of these. So it tells us we've got a mixture that's got both of them in it. And so if we want to try and solve this, like I said, I know this is a tricky problem. It's going to be a system of equations problem where you're going to need to start writing algebra equations for everything that we know, and then see how many we can get and see what else we can do. One of the things that people forget is that these balanced reactions are a bunch of conversions, right? When the conversion is an equality, meaning it is an equation if you write it properly, right? Because you can say something like, for every 1 mole of propane, 3 moles of CO2 will be made. Which means we can make an algebra expression for moles of everything that's related to these coefficients. These coefficients are the rest of the information you need, and a molecular weight, a couple molecular weight calculations. And so the easy one is mass total is 3 grams, right? Just checking my sig figs. And we know that that's the mass of methane plus the mass of propane. The other thing that we are told at the beginning is that so we use the, I'm not sure if I've officially introduced this yet, the variable for moles is lowercase n. Right, so we can say that the moles of water at the end is 1.75 times moles of CO2. And so far, other than the fact that I used n as a variable, nothing is, so far, is that tricky, right? This is one of those, like, write things that are so dumb that you can barely stand it, but turn it into an algebra expression and it counts as an equation. However, the problem is that right now, let me just erase this, so when we're counting variables, we don't count that. We have 4 unknowns. We need more equations. If we only have 2 equations and 4 unknowns, we can't solve anything. So we need something that's going to allow us to compare masses of propane and methane and moles of water and CO2. So the first 2 that are we're going to get from the stoichiometry are related to moles of product and then moles of reactant that we started with.
So moles of methane and propane.
Because where is all of our CO2 coming from? Oxygen and these 2, right? So we know that we don't know how many moles of CO2 we have, but we know that all of it is coming from one of these 2 places. Our total moles of CO2, how many moles of CO2 can come from methane? Like, what's the ratio? 1 to 1, right? So for every 1 mole of methane that we have, we know we have to be making 1 mole of CO2. Where's the rest of our CO2 coming from?
Propane.
Propane, and in what ratio?
1 to 3.
1 mole of propane makes 3 moles of CO2, right? So for every 1 mole of propane, we're making 3 moles of CO2. If you're not sure about that, about writing it that way, it should be multiplied by 3 or divided by 3. Instead of doing it as a variable, just pick a number. Say, okay, let's say I have 0.5 moles of propane. How many moles of CO2 is that? Well, 1 mole propane. I'm just going to blank this now so that I can use the whiteboard space. One mole of propane is going to make 3 moles of CO2. Is the moles of water from reaction 1.
CH4 over 2.
So that'd be the mole. And for every 1 mole CH4, 2 moles of water, right? So does that help? Instead of just throwing it in as a 3, I'm just writing out the stoichiometry conversion in my algebra expression to show the units. Does that make sense? Everybody see where I'm going with that?
But that would leave you in moles of water.
That's what we want, right? That's what this equation is moles of water.
Okay.
So if we take moles of methane and we multiply by 2, that's how many moles of water we get from the methane once it's burned. So we want it to leave us in moles of water. And then moles of propane, it's 1 to 4, right? So in the interest of simplifying this, you could, once you write it out, once it makes sense to you, you can take this and you can just turn it into coefficients in front of your variables to make the equation look cleaner. But all we really are doing with this is we're using variables to do stoichiometry because we don't know what those numbers are yet. But it's still a true equation because we know all of the water has to come from one of these two sources and in these specific ratios. So that just got us to 4 equations. How many variables do we have? We had 4.
Now I have 6.
We added 2 variables when we did this though, right? Because our mass equation is the odd man out at this point because we don't have anything else that's in mass. So we have 6 equations, or 6 variables right now. But if we can find some way to turn these into moles, then everything's connected. So what do we know about the mass of methane compared to the moles of methane?
Well, 1 mole of methane equals 16.05 grams.
We've got grams per mole from the periodic table, right? Same way that we used variables and regular stoichiometry conversions to write an algebra expression, we can do the same thing with masses and moles and grams per mole, right? So we can say, okay, well, I don't know how many moles or how many grams of methane I have, but I know that whatever moles of methane I have, if I cancel out moles and use the molecular weight, I can be in grams, right? And methane CH4, so 16.05, I think.
Yeah.
And again, this is sort of like when we're working in Excel. Sometimes it's harder to see it as a formula than it is to do it with one of your data points. So we don't have any data points, but if you want to know how do I convert from mass to moles as a general formula, pick a number for moles. Say, okay, I'm starting with 2 moles of methane. How many grams is that? And whatever math you do, if you can write it out as algebra with an unknown number of moles, that's an algebra equation. And we don't know what either of these are, but we know this is true. That got us to 5 equations. So what's the last one?
Do the same thing for propane.
Yeah. The other odd man out in our equation 1 was mass of propane. We know the formula of propane, so we can do the exact same thing here. Our mass of propane is equal to moles of propane times 44.
Yeah, 0.01.
There's our 6th equation. And when you see them all written out as equations, it can look intimidating, right? Because sometimes 2 equations, 2 unknowns can look intimidating to try and solve it. remember how simple some of these equations are, especially if we get rid of the units and the conversions and just simplify it to make it look cleaner. We can do, some of these substitutions are really fast and easy, right? Plugging these two into equation 1 and getting rid of all of your masses is then we just already got rid of 2 equations and 2 unknowns. And same here, if we have moles of CO2 and we just plug it in there, plug all of this in for moles of CO2, and plug all of this in for moles of water, we just got rid of 2 more variables. And now we're down to the only 2 variables left are moles of methane and moles of propane. And now it starts, you know, you have to follow the algebra through. But getting here, these 6 equations is the trickiest part. The rest is just plug and chug. Keep going, keep simplifying, keep substituting. You wind up, I believe, the final answer for mole or for mass of methane is somewhere right around 2 grams. And so just in the interest of
following it through.
Well, so I was going to, I'm gonna let you do the substitution, but just writing them out more simply so that it looks cleaner would be 44.01 moles of propane and 16.04 moles of methane. And then we can simplify the stoichiometry ratios here, just rewrite it as 2 times moles of methane plus 4 times moles of CO2, or sorry, of C3H8.
That wouldn't leave you in moles of H2O, would it? Okay.
So I
see.
I just erased the units to make it look better for actually doing algebra, because you don't want to have to write out that whole conversion every time you do a substitution. It'll be long enough and enough pages of paper as it is. So while you may not be able to get to this point on your own at this juncture, hopefully you have enough experience with algebra now and doing substitutions in this class that from here you should be able to solve it. Remember, just anytime you can say 2 things are equal, you can just plug it in. And I will never ask you to do anything like this on a timed test.
Timed.
On the timed test. On the take home, this is fair game.
Oh.
This will be one of the harder questions on the take home, will be something very similar to this. Probably maybe not 6 equations and 6 unknowns, but you know, this is not the first time we've seen this, right? We've done it with 4 equations, 4 unknowns. We've done it with 3 equations. Now we've done it with 6 equations. Nothing really changes other than you just got to start writing stuff down, right? And get as many equations as you have variables.
And we're going to get the take-home exam and the regular exam.
So yes, good. This is a good time to talk about that. So next week is our last week of lectures. The week after that is finals week. So next week you have an ICA on Monday or Tuesday, and that's just your practice test, just like we did before the midterm. And then on Thursday, I'll hand you your take-home test. And take-home tests are, we'll talk about the rules at that point when I give it to you, but essentially you are able to still work in groups. You still just need to turn in your own work. You can check your answers with other people. You're not allowed to copy from other people. You turn it in, and you're saying you understand it and you did this work. So it can be helpful so that you're not tempted to copy, to work on it. If you're working on it with a group, kind of sit as far away from each other as possible so you're not looking at each other's papers. You're not tempted to. If somebody's trying to explain something to you, make them, you should be able to do that verbally, not just look how I did it. Right? So that usually, if you can do that, then you're not going to be in trouble for plagiarism on the take home. And you're allowed to work together as long as you're doing your own work. And I'll reiterate that, and it's all written on the take home as well. And then the take home, you will have a total of 7 days. It'll be due Thursday of finals week at midnight. So the very last day of finals week. I'll give you as much time as possible. You get a whole week to work on it.
And what day is the final in this class?
The final is also on Thursday. But if you would like to take it earlier, you can arrange to do so with me ahead of time.
And also, what time?
Same time as class.
I see.
So today is Thursday, right? So 2 weeks from today. Same bat time, same bat channel. Anybody actually ever watched the old Adam West Batmans? They're awful.
Oh yeah,
They're wonderfully bad.
Pretty much the only thing I ever remember from seeing that show is the bat shark repellent.
Bat shark repellent. The bat nuclear reactor that powers the Batmobile. All right, let's go back to slides. All right, so we're gonna skip random applications today to get into gas laws, because the faster we get through this material, the more time we'll have for review a week from today. So you have this lecture, then we'll have a lecture of new material on Tuesday, and then maybe half a lecture that'll be mostly practice problems on a week from today. And it'll also be a chance to review, go through the practice test, just like we did for the midterm. All right, so this setup should look pretty familiar, especially for those of you who just finished lab half an hour ago. This is basically what we did. They just have, it's not a syringe, they actually have a real piston. But it's showing the same thing. If we have a fixed number of gas molecules, all moving at the same average speed, and we compress it, we're decreasing the area, right? Same force, less area. So what should pressure do? Pressure should go up when we push down on it. And we demonstrated that when we plotted 1 over volume versus pressure, and we got a straight line. That tells us that we have this relationship between pressure and volume. We can't say pressure is equal to 1 over volume because there's a slope involved, right? But we can say that it's proportional to 1 over volume. And if we did our job better in, we're more careful and we took into account friction better in lab, the equation for the line for pressure versus 1 over volume should have gone right through the origin. Because when pressure goes up to infinity, that's when volume was getting close to 0, right? When volume is getting close to 0, when 1 over volume is getting close to 0, that's because volume is getting close to infinity, right? So at this point, if you could actually get to 0 pressure, it would be when your volume was infinite, which is when 1 over volume would be 0. Right, so this symbol, it looks kind of like a fancy alpha, Greek letter alpha. It means is proportional to, which is not the same thing as saying it's equal. It means it's that when you plot these variables, you get a straight line that goes through the origin. In other words, you get an equation. It means that pressure is equal to 1 over volume times a constant. We don't know what that constant is, but that's effectively the slope of our line. Right? If the slope of your line is 1 to 1, then we would just get pressure equals 1 over volume. But depending on what units we pick, the slope is not going to be 1. At the slope for the units that we had in lab, the slope was like 10 to the 7 or something like that, right? So we don't just say pressure is equal. We use this symbol to say that they're directly proportional. And that means we can do some interesting things with this equation. Right? Because if we say that for a certain closed system of gas, like our syringes, the pressure is equal to a constant times 1 over volume, we can do some algebra, put that constant by itself. We get pressure times volume equals a constant, right? Which, again, is not entirely obvious why that's all that helpful, except for the fact that this means that any combination for this system, any combination of pressure times volume has to equal the same constant. Which means we frequently write like this. So it's called Boyle's law. Boyle's law is basically for a closed system of gas at a constant temperature, pressure times volume is always equal to the same constant. So you can make changes to a pressure or a volume and predict what happens to the rest. All right, so P1 V1 equals P2 V2. So if the pressure is doubled, what happens to the volume? That would be if it was directly proportional, and doubling one doubles the other. If they're always going to be equal to the same constant, then when one goes up, the other has to go down. So if your pressure doubles, your volume's cut in half, and vice versa. And we can do it with numbers that aren't so intuitive. We say we have a volume of 2 liters, and it's sealed at atmospheric pressure at sea level, and then we compress it to 1.65 liters. What happens to the pressure? Well, this has a lot of variables involved. That just means I've got to give you lots of information, right? So P1, we'll just call that the initial. P1 is 760 torr. And V1 is the volume that goes with that pressure. Those are paired together, right? This is before anything changed. So V1 is 2.0 liters. For the sake of sig figs, we'll add another 0 there. And then we compress it to 1.65 liters. So what else do we know?
P2.
V2. V2 is 1.65 liters. We're trying to find P2. It doesn't matter which one you call 1 and which one you call 2, right? Mathematically, it doesn't make a difference as long as you keep them paired together properly. This is the pressure at this volume. We want to know the pressure at this volume. So actually plugging these in, we get 760 torr times 2.00 liters equals P2 times 1.65 liters. Get something like 900?
921.
Right? Just multiply these together and divide by 1.65. solves for P2. Does it matter that we're in torr? We could do this just as well with pascals or atmospheres or PSI or whatever we want, right?
As long as the other side's in the same unit.
As long as the other side's in the same units. So as long as your units are consistent, we can't do this with liters and gallons. Right? Because then if we actually tracked our units through when we did our math, we'd get torr times liters divided by gallons. And we want the two volume units to cancel each other out when we solve. And so for these simple gas laws, it's going to be a common, we're going to go through a bunch of variations of this that all look pretty similar. And it doesn't matter at all what the units are as long as they're the same. Well, except for temperature, but temperature's special. All right, so so let's say that instead of changing pressure, we're going to change temperature. So, and since it's not really safe to heat a closed container of gas with a fixed volume, we will let the volume change for this one. So this is Charles' law. I don't think Charles Boyle from Brooklyn Nine-Nine is a reference to gas laws, but now I'm second guessing that because Charles and Boyle's are the first two laws that you learn in gas laws. What would we expect to happen? At the molecular level, what happens when we increase temperature?
Stuff moves faster.
Yeah, stuff moves faster. If it's moving faster, what happens when it hits the wall? What happens to the force when it hits the wall?
It's increased.
The force is going up, right? The size of the molecules isn't changing. But if they're going faster, when they bounce off the wall, there's more acceleration, which means your force gets bigger. So for the same number of molecules, they're going to push harder, which means if we're letting the volume expand as much as it wants, so that it keeps a constant pressure versus the outside world, what should happen to the volume when we increase temperature?
It goes up.
Should go up, we would expect, right? And if increasing the volume or increasing the temperature increases the volume, we're probably not going to have an inverse relationship, an inversely proportional relationship, like with volume and pressure, where one goes up, the other goes down. So hopefully we get a simpler function, right? And so when we actually do this experiment, you start at 0 Celsius and you gradually increase temperature and watch the volume. It goes up in a nice clean line. But it's not proportional though, right? The equation for this line is not as simple as something that goes through the origin, right? For it to be a nice clean equation, we don't want an intercept. Right? Because the equation for this line would look something like volume equals slope times temperature plus a constant. That's not going to be nearly as useful to set up an equation like P1 V1 equals P2 V2, right? When you have to include addition and subtraction in there too. So when this happens, what does this suggest though about if there's a y-intercept? What else do we know about this graph? There has to be an x-intercept over here, right? There has to be something way over here where volume goes to 0.
So we have our temperature.
So what if instead of starting at 0 Celsius, what if we called the x-intercept 0? If we just shift everything over, instead of starting at 0 Celsius, we're starting at 0 Kelvin. This is actually where Kelvin first came from. The idea of absolute zero came from this experiment, because they said, well, there has to be some point where you get to 0 volume, and you can't go to less than 0 volume, right? It doesn't make any sense. So you also can't get colder than that. So this temperature that they called absolute zero is the point where all motion stops. And all motion stops, you can't have any volume for a gas. Really, you can't have a gas. We can't actually ever reach that, but that gives us a point where we can just set our temperature scale.
You can get very close, though.
Very close. Liquid hydrogen boils at 2 Kelvin. But you can get a lot colder than that if you take something that's already really cold, and you can actually cool things with lasers. If you can control their wavelength very closely, very carefully, you can actually get them to get even colder by shining a laser on it.
Sound right.
It doesn't, but it's a little bit like if you think of making things warmer with a laser as when the atoms are moving towards you, you then push it, like push a kid on the swing. You can make the kid go higher if you time your pushes right? But if you time your pushes a little bit differently, you can make them slow down. So by modulating the wavelength of the light to be just right, just barely off of the normal frequency the atoms vibrate at, you can actually make them slow down by shining light on them, which again sounds backwards. Does not seem like it should be possible to add energy to slow something down. But think about the kid on the swing analogy. That's what you're doing. You're putting energy in while you're expending energy to pull energy out of the kid swinging. So that's how they get colder than liquid hydrogen boiling is about the coldest you can get using naturally occurring phenomena. We just have other ways we can tweak it to get even colder. But nothing's ever gotten all the way to absolute zero, because if you actually had something at absolute zero and then you measured it, unless the thing that you're measuring with is also at absolute zero, you just warmed up your sample. And whatever's touching the thermometer also has to be at absolute zero. And whatever's touching that has to be at absolute. You see how this works, right? If you could actually ever get to absolute zero, it would be very short-lived, because something's going to bump into it. And the second you bump into it, there's some motion. Because how else do you bump into something if you're not moving?
Would the heat death of the universe lead to absolute zero?
No, it goes the opposite direction. Heat death is when everything has the exact same temperature and is equally spread out from everything else. So nothing ever happens because everything has the same energy as everything else. But it wouldn't be at absolute zero. Although if you make the assumption that the universe has an infinite size, then maybe. I'm not a cosmologist though, so I'm not the right one to ask. If we double the absolute temperature, what should happen to the volume? Should also double, right? As long as we're going through the intercept, as long as we're in Kelvin, doubling the temperature should also double the volume. So that means you have to be careful with your units now. Like I said, temperature is the special one. Volume and pressure, we don't care about what units we have as long as they're the same. But temperature has to be in Kelvin for these to work. And this is just another version of the same derivation we just did. If we say the volume is proportional to temperature, that means volume is equal to a slope times temperature. If we rearrange that, we get volume over temperature equals constant. And therefore we could say, just like P1 V1 equals P2 V2, we can say for a closed system at a constant pressure, volume divided by temperature is always equal to that constant. So V1 over T1 equals V2 over T2. So if we wanted to find the volume of and I think we need to add more sig figs to the volume here for it to be measurable. If you have a 10-liter system, if V1 is 10.00 liters, and T1 is 22 Celsius, and we heat it up to T2, which is 51 Celsius, what's our new volume going to be? Well, we have to put these in Kelvin first. Luckily, that's a pretty easy conversion, right? No multiplying involved. Just add 273. So we get 295 Kelvin. And for whatever reason, when we write Kelvin as a unit, you don't write the degree sign. Although I think I figured that out the other day.